So hello Year 13, and sorry that I'm not there with you in person, but due to the Olympiad in the morning and the fact it's period 5 and your eyes are probably very tired, I thought I'd do this as a pre-recorded lesson so you can watch this in your own time. So we're going to keep going with the spec points that we were looking at in the first lesson this week, and that is these. Be able to record observations and write suitable equations for the reactions of chromium, iron 2, iron 3, cobalt and copper with aqueous sodium hydroxide and aqueous ammonia, including in excess. And we started to look at those reactions with copper in the first lesson this week. Be able to write ionic equations to show the difference between ligand exchange and amphoteric behaviour. Okay, so that is acid-base behaviour. It's a bit more sophisticated than that, and we will look at that in more detail possibly next week, possibly the week after. But ligand exchange versus acid-base behaviour. There are 4 reasons that you need to know why a complex may change colour. So when transition metals take part in chemical reactions, there can be a colour change due to a variety of different things. Firstly, redox, a change in oxidation number of the metal ion. 2. Acid-base, the ligands gain or lose a hydrogen ion. 3. Ligand exchange, one or more of the ligands around the transition metal ion is replaced by a different ligand. Or 4. Coordination number, the number of ligands changed. Now you should be able to give me an example already of each of these reactions giving you a change in colour. So pause the video and see if you can find an example of each. Okay, so colour change by redox. The most obvious one, the one that I really hope that you remember from GCSE, is that iron 2 solutions, particularly iron 2 in water, is pale green. So this here, iron or hexa aqua iron 2, hexa aqua iron 2. Whereas if that oxidizes up to iron 3, which it does naturally in the air, when iron goes from the 2+ to the 3+ state, then that results in a yellowy brown colour. And remember this from your GCSE precipitations, as these colours were used to identify these 2 ions. And a reaction, we don't normally draw it, but it would be hexa aqua iron 2 forming hexa aqua iron 3 with the release of an electron, and this is of course a half equation. Colour change by acid-base. Now you were introduced to these in the first lesson this week, when hexa aqua copper 2 is reacted with dropwise base, so not an excess, then you deprotonate 2 of the water molecules to make a neutral complex. It's no longer a complex ion, it's just a complex. And that is a solid and it precipitates out. Here you can see on the right hand side the conjugate acid formed when those protons are removed, and that example you encountered in the first lesson this week. Colour change by ligand exchange. Well, again, you have seen these several times, but if we are just talking about exchanging ligands without coordination as well, then we're slightly more restricted in what we can show, but adding excess ammonia, we can swap 4 and only 4 of the water ligands to form this in fact I've written up here, tetraamine diaquacopper 2 species, which is a much deeper blue colour than the hexaaquacopper 2 complex. And again, you saw that in the first lesson this week. As I said here, colour change by coordination. It is difficult to find examples of changes in coordination number that do not also involve changes in ligands. Normally you get a different coordination number because you are swapping the ligands. And in particular, we've talked about the fact that the chloride ion is a large ligand. And therefore you can rarely fit 6 chloride ions around something. And again, reminding you that the 2 examples that you should know are that when you take hexaaquacopper 2 and react it with chloride ions, you get tetrachlorocopper 2, which is a yellow colour, but sometimes you'll see the green solution, which is a mixture of the 2. And the other example that you should be familiar with is that cobalt, hexaaquacobalt 2, is a pink colour, whereas tetrachlorocobalt 2 is a blue colour. And you've encountered that a couple of times, not least in the idea of cobalt chloride paper. As a test for water. And again, in the middle of this, you will end up with a purple solution, which is just a mixture of the 2 different species. So you go through purple as you change from one to the other. Now, we're going to go through cobalt, iron and chromium, and in all of these cases we're going to react these with alkali. So let's remind you what happened with copper first. When we added ammonia or hydroxide dropwise, we ended up with a precipitate. The addition of excess hydroxide made no difference to that precipitate, but the addition of excess ammonia did affect it because the precipitate redissolved to form a dark blue solution. Now the reason for that is in this first step we've got acid-base behaviour, while here we have ligand exchange. Okay, the hydroxide does not complete ligand exchange, but the ammonia does. So let's have a look at hydroxide and cobalt. So you can see here that the cobalt is producing a blue precipitate, so a sort of reddy pink solution initially. As the hydroxide is added, it is forming a blue precipitate, but we can see even in the time that that precipitate is sitting there, the stuff at the bottom is turning pink. And if we do this in a time lapse, we will see that all of that blue precipitate is turning pink. So, pink solution, cobalt 2, adding hydroxide dropwise gives us a blue precipitate. That blue precipitate, if left to stand, will turn into a pink precipitate naturally. And when we add excess hydroxide, just as with the copper example, there is no change to that pink precipitate. And again, we can assume that probably what's going on here is acid-base behaviour. And you could probably begin to write an equation for this reaction. So cobalt H2O6 2 plus 2 hydroxide aqueous is forming cobalt H2O4 OH2 neutral, which is why it precipitates out. It no longer binds favourably to water, and to H2O liquid. What happens if you take that pink solution and you react it with cobalt 2? So if we add the ammonia dropwise, we get a precipitate. Now it looks green in this video, and it is slightly greener, but it is actually the same precipitate. So we're still forming that same blue precipitate, but we get that solution. For adding excess ammonia though, and here they've decided that the solution isn't quite, or the jar isn't quite big enough to add excess ammonia, but we can start to see that some of that precipitate is dissolving. So zooming out here so that we can see a little bit more. With excess ammonia, the precipitate, just like with the copper, it is dissolving, and we can presume that some form of ligand exchange is going on in this situation. There we go. And with enough ammonia, the precipitate is dissolving quite nicely to form a reddy brown solution.
I'm going to add the same ligand to both of them.
Now if instead we just add excess ammonia directly, we don't go through that intermediate precipitate, the green precipitate, we just go directly to that red-brown solution that you saw at the end. Now, leaving that red-brown solution, it would naturally do this, but this is speeding up the process, reacting that red-brown solution directly with oxygen, and we can see a change in colour as the cobalt 2 plus is oxidised to the cobalt 3 plus, okay? Now this doesn't happen with the hydroxide solution or the hydroxide precipitate, but when you end up forming that solution, the cobalt 2 ammonia solution, that will oxidise back up to cobalt 3. Okay, so back to this idea. We add hydroxide to cobalt, we get a blue precipitate which rapidly turns pink, and excess hydroxide does nothing. We add ammonia, we get the same precipitate, even though it technically looks greener, but excess ammonia will cause that precipitate to redissolve to form a red-brown solution. And again, we can presume that this is ligand exchange. If you leave that red-brown solution for long enough, or you add oxygen, then it forms a much darker solution, a dark brown solution. And this is redox. And this is due to the cobalt 2 plus being oxidised up to cobalt 3 plus. So let's see if you've taken that in. Here we've got the reactions of cobalt, starting with the pink hexa-aqua cobalt 2. On the top, adding sodium hydroxide. On the bottom, adding ammonia, a small amount followed by an excess. Classify each of those 4 red arrows as redox, acid-base, ligand exchange, or a change in coordination. So these 4 things we saw at the beginning of the video. Which type of reaction is each of these? Pause the video, have a think. Okay, well, just as with the copper solutions that we saw in the first lesson this week, the initial thing that happens in both cases is an acid-base reaction forming the neutral solution. Okay, so this is neutral, and that is why it is a precipitate. And again, this is neutral, and that's why it is a precipitate. It doesn't bind favourably to the water if it's not charged. On standing, this is just a weird quirk, so don't worry too much about what's going on here. But here, with the excess of ammonia, we can classify this, just as with the copper, as a ligand exchange. However, unlike the copper, which has the Cu2 plus ion is 4s03d10, it would be unfavourable to remove another electron. The cobalt 2 plus ion is 4s03d cobalt 7 3d7. So there's no such hindrance here to removing another d electron, so this will oxidize while the copper 2 plus won't. So that there is an example of a redox reaction. So acid base at the top, acid base bottom left, ligand exchange down here under my scribbles, and redox. Okay, all of these are hexa or octahedral complexes, sorry, so they are all 6 coordinate. If you really want to challenge yourself, write an equation for each of these reactions, because that is a skill you need to be able to do. As I've said there, the blue turning to the pink is a rearrangement of the ligands within the precipitate, and don't worry about that, you don't need to know. Okay, so this is summing up those reactions. So taking the hexa-aqua cobalt complex and adding base, you end up with a blue precipitate that slowly turns pink. It is uncharged, and I will say again that the reason it's a solid, the reason it's a precipitate, is because it is uncharged. And that will help you to work out the formula of these things if you realise precipitates are uncharged. And here on the right hand side we have the conjugate base. Sorry, the conjugate acid. Down here, for excess ammonia only, not hydroxide, we end up with a ligand substitution reaction. This time, notice that we are substituting all ligands to form a yellow-brown solution or a red-brown solution of hexaamine cobalt 2, which is oxidized in air to form a brown solution of hexaamine cobalt 3. And as I've said at the bottom, notice here that all ligands are replaced by ammonia, while the equivalent copper complex only swaps 4 of its ligands. You don't need to know why. Why is not important, but the fact that it does do this, the formulae, that is important, okay? So you do need to know the formulae that it forms, but you don't need to know why it does. It is just some factual learning, I am afraid. We're going to do the same thing with iron now.
Iron 2.
So adding hydroxide to iron 2, you can see we are getting a green precipitate that you would have used as a diagnostic test back at GCSE. Adding excess hydroxide does not affect the precipitate. It remains a dirty green precipitate that will gradually turn orange
Iron
at the
3.
top. Iron 3, the solution is a yellowy colour, and when we add the hydroxide we get that rusty brown precipitate that you will recognise from GCSE. Upon the addition of excess hydroxide, it remains an insoluble brown precipitate. And now what happens when you add ammonia to iron 2 and iron 3?
Iron 2.
Okay, so an iron 2 complex there. Adding ammonia, we get a dirty green precipitate.
Iron 3.
And now adding ammonia to the iron 3 complex, we get that rusty brown precipitate. That you can see there. And adding a bit more ammonia is making little difference. Okay, so let's cover that again. So if we take iron 2 plus and we put it in water, we sort of end up with a very pale green solution. We add some sodium hydroxide. This clearly is acid base. We end up with a green precipitate which upon standing starts to go orange around the top, and that is oxidation going on up there. Doing the same thing with ammonia, we get exactly the same result. We get this dark green precipitate. Again, we get acid-base behaviour, and upon standing, we get some precipitate turning orange towards the top where the oxygen is dissolving. If we add sodium hydroxide to an iron 3 solution, which is a sort of yellow orange colour, then again we form a precipitate. This one is orange. Again, notice that the precipitate is neutral. This time we have removed 3 protons. And that is to generate the neutral precipitate. And again, think about how you would write the equation for that reaction. Adding ammonia to iron 3, exactly the same thing. The iron 3 hydroxide, sorry, the ammonia deprotonates the iron 3, the hexa aqua iron 3 complex to form a neutral, the same neutral precipitate. And this is all acid base. So there is no ligand exchange with iron. And here are the reactions summed up for you. So with the iron 2, they react with 2 lots of base to form the neutral 2+ precipitates, and we end up with 2 lots of conjugate acid, whereas with the yellow solutions, the iron 3+ solutions, we react with 3 lots of base, again to form a neutral precipitate. There is no ligand exchange here. What you do need to know, however, is that the green precipitates will naturally in air oxidize to give you the orange precipitates. The final metal that you need to know about and its reaction with base is chromium 3. So here we go, hydroxide and chromium 3. Chromium 3 is a beautiful green solution. Upon adding hydroxide, we sort of get a grey-green precipitate here. And upon adding excess hydroxide, that precipitate redissolves. Now this is unexpected, because adding extra hydroxide did not redissolve the copper precipitate. Adding extra hydroxide did not redissolve the cobalt precipitate. It did not redissolve the iron precipitate, nor the iron 3 precipitate, but adding extra hydroxide does here redissolve the chromium 3 precipitate. So that is an unexpected result. Adding ammonia to chromium 3 now.
Chromium 3.
Again, that lovely green colour. Adding ammonia, again we get that sort of grey-green precipitate colour. And we can presume that is due to acid-base behaviour. And adding a bit more ammonia does not seem to have done something, but actually they didn't go far enough on the video. So this is what you get. Now you might be surprised to see the chromium, the hexaaquachromium complex being shown as purple here. It is pure hexaaquachromium is violet, but often it appears green due to contaminants. Okay, so the reason it appeared green in that video to start with is due to contaminants, things like chloride ions and sulfate ions in the water. As we saw, adding sodium hydroxide solution produces that sort of grey-green precipitate. But surprisingly, excess sodium hydroxide solution did dissolve, redissolve that precipitate. And that is because it further deprotonated by excess base. So again, acting as acid base to form the rather unexpected hydroxochromium 3 complex here. So it deprotonates all of the ligands, again forming a charged complex ion which redissolves. Down here, small amount of ammonia, we get acid base producing the neutral precipitate. But then, unlike the hydroxide, excess ammonia gives us ligand exchange to produce a beautiful violet hexammine chromium 3 solution. Okay, so that is a lovely violet colour. The reaction with ammonia is similar first, showing acid-base behaviour, but if excess ammonia is added, a ligand displacement occurs, which generates a soluble solution where all 6 ligands have been replaced by ammonia. And here are the first couple of equations. So reacting the green/violet, depending on which books you read and which reactions you do, green or violet hexa-aqua-chromium complex with 3 lots of base, you end up with this grey-green precipitate that you can see here and the conjugate acid. So that's what happens with the dropwise ammonia or hydroxide. But this is the difference. Excess hydroxide will generate a dark green solution because of further acid base. As I've said, this is a further acid base reaction, but reacting that grey-green precipitate with extra ammonia, then you get a ligand substitution reaction. Nevertheless, both of these complexes are charged, which is why they redissolve, one to form a dark green solution, shown here. Excess hydroxide forms this green solution, while excess ammonia forms this violet solution. Some of you are going to cry when you see this slide, but this sums up what you need to know, I'm afraid. So you do need to know both the formulae and the colours of the various precipitates and solutions formed by these 5 ions, as it says in your spec. So just to run through them, the hexa-aqua copper was a pale blue solution which formed a blue precipitate with some hydroxide. That is an acid-base reaction. Nothing happened if you added extra hydroxide, nothing happened if you left that. If you added some ammonia, you got an acid-base reaction, but if you added excess ammonia, you got a ligand exchange reaction. But notice you don't swap all ligands. Cobalt, the one we looked at the start, pale pink solution, very similar with hydroxide. It's acid base, you form a blue precipitate that does turn pink. This is just a rearrangement, you don't need to worry about that. Just like copper, nothing happens with excess OH, nothing happens if you leave it. Adding ammonia, again we get the acid base reaction, but then we can get a ligand exchange reaction to form a red-brown solution. The only difference is that if we leave it, we get redox because cobalt can be oxidized up to cobalt 3, while copper can't be oxidized to copper 3. Iron, you should know, is a pale green solution that gives you a dark green precipitate. What you wouldn't have known was that that is an acid-base reaction. If you leave that, then that will oxidize. Nothing happens if you add excess hydroxide, but if you leave it, it will oxidize. The same thing happens with ammonia. You add acid base, and if you leave it, it will oxidize up to iron 3. You don't get ligand exchange with iron 2+ or iron 3+. The iron 3+ is a sort of yellowy orange solution. Again, we get acid base, but look, there's 3 hydroxides now to make that neutral. Nothing happens with excess hydroxide, nothing happens if you leave it. If you add ammonia, again it reacts in acid base, forming the same precipitate. It can't oxidize, it doesn't oxidize, and it doesn't ligand exchange either. So that's the simplest one to understand. Chromium down the bottom, either a violet or a green solution, depending on who you ask and the conditions under which it's made. But it forms a grey-green precipitate, again, just like the iron 3+, where 3 of the water ligands are deprotonated. but this is the only one where you get something happening with excess hydroxide. You get a further acid-base reaction to generate the hexahydroxyl chromium 3 species. And that's probably not called the right thing, but you get the idea across. If you add ammonia, again you get acid-base, and as with the copper and the cobalt, you then will get ligand exchange, most similar to the cobalt in that it will swap all of its ligands for ammonia. There is a lot to learn on this slide, and it's not nice, it's not pretty, but at some stage you're going to have to sit down with a flashcard and try and remind yourself of all this stuff. But we can help ourselves out by thinking of the general principles, and they are these. Firstly, all the precipitates are neutral complexes. So if you're not sure exactly how many things have been deprotonated, well, we need just enough hydroxides to make the complex neutral. Things that aren't neutral are soluble. And that's what it says there. The charged complexes are all soluble. So all these water, the aqua complexes are soluble. All the ammonia complexes with the excess ammonia are soluble. It is just the neutral complexes that aren't. It is only the 2+ ions that oxidize in air. You can't oxidize the iron 3+, you can't oxidize the chromium 3+ in air. It is just the cobalt 2+ and the iron 2+ that oxidize. Copper 2+ does not oxidize because copper does not show the 3+ oxidation state. Hydroxide never does ligand exchange. It always shows acid-base behaviour, and in almost all occasions it just deprotonates to form the neutral the neutral precipitate. It is only with chromium it is able to go past the neutral precipitate and form a soluble complex. And I want you to think back to GCSE and which precipitate redissolved in excess hydroxide, to have a think about what might be going on there, and can you come up with an equivalent equation to explain your observation that one of your precipitates redissolved in excess hydroxide. Finally, ammonia always shows acid-base behaviour first up to the neutral precipitate, and then in some occasions it will show ligand exchange. It will show ligand exchange with copper, cobalt and chromium, but it will not ligand exchange with iron. Okay, a lot of information. You may want to watch this video more than once, but have a good weekend. There are some questions that are being sent your way for you to think at, and we will go through those questions in class next week. Goodbye.